Hello everyone. In this video we are going to discuss topic of matrices. Solution of second order linear differential equation with constant coefficient by matrix method by Suchita Mohri. This is the main application of matrices to solve the differential equation. We start with the types of ordinary differential equation. Ordinary differential equation divided into two types: first order differential equation and higher order differential equation. In this higher order differential equation, that means second order, third order up to nth order, this we called as higher order differential equation. Now second order linear differential equation with constant coefficient. Now order, what is the order? Highest derivative appearing in the differential equation, which is we called as order. For example, this is the example. Now in this equation, highest derivative is 2 and a and b, which are the constants. Therefore here this equation we called as second order linear differential equation with constant coefficient. Instead of a and b, here variable is t, suppose, then we call this equation as second order differential equation with variable coefficient. Now here we solve the second order differential equation with constant coefficient by matrix method. Now these are the important steps for solving the problems. First is we consider x equal to x1 and dx1 by dt equal to x2. Use equation number 1, and given equation we write down in the form of x1 and x2. We use equation number 2. Now by using these two equations we write down the equation in the form of this: dx by dt equal to a into x, where a is the matrix. Now for this matrix we find out the eigenvalues and then find out eigenvectors corresponding to each eigenvalue. Then we write down model matrix. Then we write down the equation in the form of x1 x2 equal to b matrix. B means model matrix, that means step number 6, and c1 e to the power lambda 1 t and c2 e to the power lambda 2 t. Here second order differential equation is there, therefore two eigenvalues. Lambda 1 means first eigenvalue, lambda 2 means second eigenvalue. Now if initial conditions are not given, then we write down the general solution, that means the last answer in terms of C1 and C2. And if initial conditions are given, then we apply these initial conditions and find out C1 C2 values and write down the last answer as X. We discuss some examples here. This is the first problem, and here initial conditions which are given here: x of 0 equal to 2 and x dash of 0 equal to 1, and second order differential equation with constant coefficient is given, because here minus 4, which is the constant value, and 3 is also constant value. Now here first step is x equal to x1 and dx1 by dt equal to x2, gives equation number 1. Then we write down this equation, given equation, in this form. Here this d2x by dx square we write down in the form of d by dt into dx by dt. Second term as it is, third term as it is. Now here x equal to x1, therefore we write down this x equal to x1 here. Then dx by dt, dx by dt equal to x2 by using equation 1, therefore we write down here x2 value, and this dx by dt, again this is the x2 value, because x equal to x1, therefore dx1 by dt, that means x2 value. And then we shifted this second and third term on right hand side, then we get equation number 2. Then by using equation 1 and 2, we write down this in the form of dx by dt equal to a into x, where a is this matrix. Then we find out eigenvalues of this matrix. For this, we consider characteristic equation A minus determinant of A minus lambda equal to 0. We substitute the values, simplify the terms, then we get this is the characteristic equation, and if we solve this equation, we get two values of lambda. First is 1 and second is 3. And then we find out eigenvector corresponding to these two values. Eigenvector corresponding to first value lambda equal to 1. Here a minus lambda into x equal to 0. We get these two equations, substitute here a minus lambda value. Then on solving this, we get only one equation, minus of x1 plus x2 equal to 0, because here first equation is minus x1 plus x2 equal to 0, second equation is minus 3x1 plus 3x2 equal to 0. That means if we divide by 3, we get only one equation. Therefore, these two equations are same. We consider this equation, substitute x1 equal to k and find out the value of x2, x2 equal to k again. Therefore, we write down the x1, x2 values in terms of k, divide by k, then we get the eigenvectors corresponding to lambda equal to 1. This is the first set of eigenvectors. Now similarly, we find out the eigenvector corresponding to lambda equal to 3. In this equation a minus lambda into x equal to 0, we substitute the values, we get again same equation, and this equation is given by this. Here substitute x1 equal to k1 and x2 equal to, then we get x2 equal to 3k1, and we get the eigenvectors in terms of k1. This we cancel this k1 and write down the eigen 1 and 3, which are the eigenvector corresponding to lambda equal to 3. Then in next step, we write down the model matrix. That means eigenvectors corresponding to, these are 1 1, which are the eigenvector corresponding to lambda equal to first value 1, and 1 and 3, which are the eigenvector corresponding to second eigenvalue 3. Then we write down x1, x2 equal to b into this value. Substitute the values, B matrix. Now then we write down equation 1, x1 and x2. That means equation number 4 and 5. Now after that we apply the initial conditions. If initial conditions are not given, this is the required result, x equal to x1, therefore this is the required result. But here initial conditions are given, therefore we substitute t equal to 0 here, then x equal to 2 and t equal to 0, x dash equal to 1. Then we get these two equations. We solve these two equations and find out C1 and C2 value. C1 equal to 5 by 2 and C2 equal to minus 1 by 2. Therefore, again substitute these values in the equation 4 and 5, we get these equations. Now, then we write down the final answer, which is equal to equation number 6. And x1 means x equal to x1 and x2 means derivative of this term x1. Therefore, we tally our answer here. Derivative of 5 by 2 e to the power t is this value, and 1 by 2 as it is e to the power, derivative of e to the power 3t is 3 into e to the power t 3t. Therefore, our answer is correct. X equal to 5 by 2 e to the power t minus 1 by 2 e to the power 3t, which is the required answer. Then we discuss another example, d2x by dt square plus x equal to 0. Here initial conditions are given. Again apply same method. We substitute x equal to x1 dx1 by dt equal to first equation. Given equation we write down in the form of x1 and x2. For this d2x by dt square, we write down this as d by dt of dx by dt, second term as it is, and convert it in terms of x1. Therefore, here x equal to, we substitute x1, then dx by dt, this is the value of x2. Therefore, and shifted this term on right hand side, then we get the equation number 2. And 1 and 2 equation we write down in the form of this dx by dt equal to a into x, where a is the 2 by 2 matrix. Then we find out the eigenvalues of this matrix. For this we first find out characteristic equation of this matrix, and this is the characteristic equation lambda square plus 4 plus 1 equal to 0, and lambda equal to plus I and minus I, which are the eigenvalues. For lambda equal to I, we find out the eigenvectors. We substitute the A matrix, then find out A minus lambda into X. Again we get single equation. This is the equation. We solve this equation by substituting x1 equal to k and find out the x2 value. This is the ik. Then eigenvectors are k, ik, that means 1 and I in terms of imaginary vectors. Now eigenvector corresponding to lambda equal to minus I, we get this matrix, and we observe this. Again this is the same equation, we get only one equation. This we solve this by substituting x1 equal to k1 and x2 equal we get x2 equal to minus of this value in terms of k1, and therefore 1 and minus I, which are the eigenvectors corresponding to lambda equal to minus of I. Then we write down model matrix B, 1 and I, which are the eigenvector corresponding to lambda equal to I, and 1 and minus I, which are the eigenvectors corresponding to lambda equal to minus of I. Then write down this equation in this form. Here we substitute the model matrix B and lambda 1 value I and lambda 2 is minus I. Then x equal to c1 e to the power it plus c2 e to the power minus it, and x2 equal to this value, equation number 5. Now apply the initial conditions in equation 4 and 5. If we substitute these values, that means t equal to 0, x equal to 0, t equal to 0, x dash equal to 1. Then equation 4 implies we get this equation, equation 5 implies we get this equation, and if we solve these two equations, then we get c1 and c2 values, which are in terms of I, and if we substitute these values, then x1 equal to this 1 upon 2I e to the power it minus 1 upon 2I e to the power minus it. If we taking 1 by 2I outside, then numerator value is e to the power it minus e to the power minus it, and which is nothing but the sin t value. Similarly, x2 is the, if we adjust this 1 by 2 outside, then e to the power it and plus e to the power minus it, which is the numerator term, and this gives the value of cos t. And if we tally the answer here, x equal to x1, this is the sin t value and its derivative is cos t. That means our answer is correct there for x equal to sin t, which is the required answer. In this way, we solve the problems of second order differential equation with constant coefficient by matrix method. Thank, thank you.